Swayam Prabha. Digital India. Educated India.
So let us continue with this introduction to differential geometry. So I am just trying to whet your appetite, tell you about some interesting things, okay, that you can look forward to, and which also are connected with this topic. Say something about the isoperimetric inequality and the four-vertex theorem, about which I said a little at the end of the previous lecture, okay, and I think there was we had to stop because of the next class. So I will expand upon that, okay, and then we will go ahead. So so you see the so what is this thing about the isoperimetric inequality? So we have the following physical observations, okay, and the idea is these can be explained by phenomena these are phenomena in physics. They can be explained using physical laws, okay, but then on the other hand there is a mathematical version of this, and without using any physics you can also mathematically prove them. So this gives a kind of unification, and that is kind of very important for people to understand that all the sciences are all integrated. They are all just various avatars of one single truth. So you see it in many different ways, okay. So so the first thing I can one can think of is, you see, you take so you take a loop, okay, and the idea is that, of course, when I take a loop, I mean a simple, so the technical word is simple closed curve, and it's a closed curve, which means it is the starting point and ending point are joined together, so that it's a loop. And simple is that it doesn't self-intersect, so it's not like a figure 8, okay, and such a thing has a perimeter, which is essentially the length of the the thread, if you want to think of it as a piece of thread with the ends fastened together, okay. And then there is also inside the area that is being enclosed inside the loop, okay. And the question is that what shape should the loop take so that you can maximize the area, okay. And so this means that here you see perimeter is constant, and you maximize area, okay. And why maximize area is because that is the only sensible question to ask. You can always minimize it as much to any extent that you want, because I can keep flattening this. So I can for the same thing I can put something like this, and then I can make it even more like this, okay. And then you see that the area that it encloses is kind of becoming smaller, and you can imagine that if I really stretch it out, then it will almost become 0, okay, to the maximum possible. So what we are interested in is trying to maximize the area, okay. So the perimeter, you keep the perimeter constant, okay. That means this is not like a rubber band that you can keep stretching, okay. Perhaps I need elasticity only to be able to bend it, but not to stretch it, okay. So you want to maximize area, and what is the shape that will maximize area? The shape is that of a circle, okay. Circular shape maximizes. And you can see this kind of physically also by putting such a thing on a flat surface, and then filling the area in between with some sticky liquid, okay. then you see that you should expect because of forces of surface tension or whatever that it will settle down in a perfectly circular shape. Okay, so this is something that you can physically see. Okay, and the point is that this also is mathematically true. So among all these loops which have the same perimeter, okay, the shape of the loop for which the enclosed area is maximum is that of a circle. Okay, that is the isoperimetric inequality. So this isoperimetric is to say that you are looking at various loops which have the same perimeter. Iso means equal or same. Okay, you are looking at various loops which have the same perimeter. What is changing is the area contained inside the loop. And when you have a maximum is the case of a circle, that is the only case. And for all other cases, the area is strictly lesser. Only circle gives you the maximum area. And in general, the area is always lesser than the area of the corresponding circle. And that's why it's an inequality. So it's called an isoperimetric inequality. Okay. And this is, a two-dimensional version of the issue, of the problem, which is of course a theorem. Okay. Of course, physically you can explain it using, if you want, surface tension and things like that. But there is also a mathematical explanation. And the mathematical explanation is what involves differential geometry. Okay, so it involves calculus. It involves trying to understand, why does it involve differential geometry? Of course, it involves calculus. See, somehow you can see that it's the shape of the loop that matters, and the shape of the loop is basically the curvature of the curve, which gives the loop, or which the loop gives. At every point of the curve, the curvature is changing. That's what determines the shape. So you have to really somehow, try to link this curvature to this property. You have to link the shape of the loop is controlled by the curvature. You have to link that curvature to the area inside the area enclosed by the loop. So you see, because you are going to involve curvature, this is going to be a subject of differential geometry. Okay, so there is something physical that is going on, and there is also something that the same thing can be theoretically formulated and proved in mathematics. Okay, so that's the kind of unifying thing that you appreciate. Okay, and this is the two-dimensional case. There is also a three-dimensional case. So, but before I go to the three-dimensional case, let me give you an alternate version of this. Here what I am doing is, basically I am keeping the perimeter constant and I am trying to maximize area. Okay, I can do another thing. I can keep the, I can try to keep the area constant. Okay, and then try to change the perimeter. Okay, and then if you do it that way, what will happen is that if you keep the area constant and try to change the perimeter, what will happen is that you should try to minimize the perimeter. Okay, so the alternative version is, what you do is that you fix the area. Okay, that is, you make area constant. Okay, and then what you do is that for all figures that have constant area, you measure the perimeter of the boundary. Okay, so, and you measure the perimeter, so it's just some area. An area can be given so many shapes, or you can find many shapes for a given area. The area is the same. Okay, so you can call it isoareal if you want, or equiareal if you want. All right, but then what is changing is the perimeter. And then what do you do with this perimeter? You should try to minimize it. Why minimize? Because if you try to maximize it, you can maximize it to infinity. You can maximize it to infinity. Okay, the only thing that you can sensibly ask is that you can minimize the perimeter. So you should understand this difference. If you keep the perimeter constant, then the area inside the loop is changing, and you have to maximize the area, and that is attained only for a circle. On the other hand, if you keep the area constant, and try to change the shape, then the perimeter will change, and then you have to minimize the perimeter, and again that happens only for a circle. So if you minimize perimeter, then what happens is that again the circular shape minimizes. Okay, and you know you can easily you can see why the perimeter can be made larger, okay, for a given area, because as you if I do this kind of thing and flatten it out for a given area, I can keep on increasing the length of the curve, okay, and therefore in principle it can go to infinity. Okay, so the sensible question to ask is to minimize the perimeter. Okay, so there are two versions. Either you keep the perimeter constant and maximize the area contained inside, or you keep the area constant and try to minimize the perimeter of the boundary. In both cases, it's only a circle that will give you the the right optimum extremum. Okay, so now this is, of course, this is in 2 dimensions. Now there is a 3-dimensional version of this, and in fact, as you can expect, in mathematics there is also an n-dimensional version of it. Okay, and that's also true. Okay, so this will lead into a branch of mathematics called functional analysis, if you want to really prove it in an extraordinary generality. Okay, but the root is something that's very physical. Incidentally, there's one more. Before I go to the 3-dimensional case, I want to tell you something of a mathematical formalism, which is the idea of measure. Okay, so in 1 dimensions you have intervals. It's just a piece of a straight line, and you measure length. Okay, and so we say 1-dimensional measure is length. In 2 dimensions you have regions in the plane, and you measure area, and that is called the 2-dimensional measure. If you go to 3 dimensions, you have volume. Okay, then that is called the 3-dimensional measure. So in this 2-dimensional case, what you can see is that there is a 2-dimensional object, which is this amoeba like thing, okay, which consists of the string and or the loop with the area contained inside. And what are the 2 objects you are trying to relate? One is the perimeter, the other is the area. And what is the area? This area is actually the 2-dimensional measure. It is a 2-dimensional measure of the interior, because the interior is a region in the plane. Okay, by interior I mean you can forget the boundary, which is the loop. Okay, anyway, the loop is just it's a thin. It's supposed not to. It's a thin thing. It's not supposed to contribute to area. The area should be only the area inside. Okay, so there is the area is a 2-dimensional measure. What about the perimeter? The perimeter is, you see, the loop is a boundary of this region, and the boundary is 1-dimensional. It's a curve. So length makes sense, and length is 1-dimensional measure. So this perimeter is a 1-dimensional measure. Okay, and the relevance is that the boundary is a 1-dimensional object, so its measure is 1-dimensional. That's your perimeter, that's your length. And what is inside is a 2-dimensional object. So what is relevant is area, and that's a 2-dimensional measure. Okay, so basically what you're doing is, if you look at it from this point of view, what you're doing is you're taking an object, you're trying to compare the measure of what is inside to the measure of the boundary. That's what you're doing. Okay, and if you try to do this in 3 dimensions, what are you going to get? In 3 dimensions, I can think of similarly a closed surface. It will contain a volume inside. The volume inside will be the 3-dimensional measure of what is inside, and then the surface will be a 2-dimensional object. Okay, and its measure will be area, and it will be the surface area. So I will have to relate the volume inside, which is 3-dimensional measure, to the surface area, which is the 2-dimensional measure of the boundary. Okay, and again you have the same kind of thing. You have the same kind of result. So if you keep the so what I can do is I can keep the surface area constant, and look at various shapes and try to maximize the volume, okay, and as you can guess, you will get a spherical shape. Okay. The other thing that I can do is that I can keep the volume constant and try to change the surface that's enclosing it and look at its surface area, and again then I will have to minimize that, and again it's the spherical shape that will give you the optimal geometry. Okay, so that's what happens in 3 dimensions. And for example, this is why when you for example blow a bubble, it automatically assumes a spherical shape if you neglect all other factors, or if you have a water droplet in space, it takes a perfectly spherical shape. Okay, there of course you can always explain it away with surface tension and things like that, but mathematically also it has a meaning. So there also you have results of this type. Okay, so let me just write that down. The 3-dimensional version is you take a closed surface enclosing a finite volume, you fix the surface area of the boundary surface, and you maximize volume. So let me write it correctly, maximize. Then you get maximum only for a sphere. Okay, and the what is the alternate version is that you fix a volume and change the outer surface, okay, and try to minimize the surface area, then again you will get only a sphere. Okay, so or you fix volume contained and minimize surface area, and you will get minimum for a sphere. Okay, so this so you see that there is now a nice analogy, and now having said it like this, you can do the same thing in n dimensions. You can take an n-dimensional object whose boundary is an n-1 dimensional object, and then you can have 2 versions of this. What shape will give you the maximum or the minimum? Okay, and again you will get something that is spherically symmetric. So let me get back. So you see this is one of the nice things, that you are able to unify something that's happening in physics physically, and with something that's also independently of that happening in mathematics. And again it's geometry, it's differential geometry that gives you this the proof of that thing in mathematics. Okay, and we are going to do it, at least the curve case, we are going to do this isoperimetric inequality for curves in this course. Okay, incidentally, yeah, so it will come in a later lecture, but of course to do it properly in the course, you will have to quantify many things. You have to understand what curvature is and so on and so forth. So there's some theory and some background that needs to be covered. We'll do that. Okay, but this is an interesting thing. So you see, the aim is in these initial lectures is to tell you that there are lots of phenomena in nature that are actually connected with this subject. All right, so that is one thing. Then the other thing I want to talk about is the four-vertex theorem. Okay, so what is happening in the case of the four-vertex theorem? So this was due to an Indian mathematician, Shyamadas Mukhopadhyay. I think in 1900s, 1901 or 1900s. I'll just put 1900s. You can look at the web. Early 1900s. Okay, so it has a 100-year history. Okay, so what is this four-vertex theorem? If you want to say it in a very loose way, it's a very simple thing. I start at a point, and then I start going in a certain direction. My aim is to return to that point, and if you think in a very naive way, you have to turn at least at four places to come back. Okay, and of course this is fraught with lots of vagueness. Okay, so I am of course assuming that I'm turning only every once only in 90 degrees. All right, otherwise I could have gone triangularly and come back. All right, but there seems to be an inherent confusion here. All right, but how do you make sense of this? It is if you can really make the right sense of this if you use the language of differential geometry. That is the right language in which this can be explained and it can be proved. Okay, so the truth is that this theorem has a 100-year history, centuries history, and then its converse has also been proved, and it's one of the most beautiful theorems, and it has generalizations in other branches of geometry. Okay, so let me just say something. You can immediately ask me that why can't I start here and then go like this, simply go on a triangle like this, and then I come back, and this seems to have only 3 turns. Okay, and of course I could have done something like this, namely I could have just kept turning all the time. Okay, and I could have come back to the same point, but you need to distinguish all these cases. So the idea is that you have to make sense of what a turn is along a path, and then the question is how many minimum number of turns you have to make to get back to the original point. Okay, minimum number of turns. All right, and I can easily dismiss any issues with any curve which contains a portion of a circle, because when you're going in a circle, okay, what is happening is that at every point you're turning, and therefore if you take all the points where you're turning into consideration, there are already infinitely many points. So that's not really an issue. The issue is to turn at minimum number of points. So the idea is, what do you mean by turning? Okay, that is really the issue. See, many things in English, when we say them, they are very, very vague, but then mathematics gives you a way of trying to concretely quantify them, which means you define them. Okay, and here what comes to our aid is the idea of a curvature. Okay, so basically what happens is that, you see, what does turning mean? So you see, you think about it intuitively. How do you turn? You're going, okay, you decide to turn, then what you do is you start turning, and then you turn more and more and more up to some point when you think you've turned enough, and then you start going back again along. You stop the turning, then you start going back, turning less. Okay, so you can see that when this turning is happening, there is some portion where you are going, you're increasingly curving more. Then at some point you have curved to the maximum possible, and then you're curving less, and then this is how a turn is made. Now think of it in terms of curvature. What is happening? Slowly, as you approach this turning point, what is happening is that you're turning more and more sharply. Therefore, your curvature is increasing. Okay, if I draw at a point of the curve which is like this, which the curvature will be very large because the fitting circle will be very large. Okay, as I come closer to here, my circle becomes smaller, and maybe here it becomes very small, the circle of curvature, which is a bit. So the more the curvature, the circle is smaller, and in fact the radius of the circle of curvature is actually the reciprocal of the curvature. So you see the if you have more curvature, then you should have less radius. You will get smaller and smaller circles. So basically what is happening, your curvature, so if you look at it like this, the curvature is increasing before the turn, and then it kind of has a maximum, and then it's again decreasing. So do you see that the curvature function is having a local maximum there? Okay, that's the point. And how do you, but this is a completely mathematical thing. A local extremum. So take the curvature function, take a local extremum for the curvature function. That's what is called a vertex. Okay. And what the theorem says is that if you take a nice smooth curve, closed curve, it should have at least 4 vertices. At least. You cannot have 1 or 2 or 3 vertices. In other words, if you try to have only 1 or 2 or 3 vertices, you will not come back to the starting point for sure. Okay. You need a minimum of 4 vertices. Okay. And here, of course, this is a sharp turn that I have made, and here your curvature increases to a maximum and then decreases. Okay. You can also kind of, if you turn too much, you might want to turn back. Okay. And then you will have the reverse of this. Okay. And that will also that can also be thought of as getting a minimum for curvature. So basically, these are maxima, minima of curvature. These are the vertices, and they are all critical points, maximum, minimum. Okay. So these are called vertices, and the theorem is that there are at least 4 vertices. Okay. It's a beautiful theorem, and yeah, but so if you ask the question that what happens in the case of a soft triangle like this, then it has to be, you have to analyze it, and you will see that there will be some portion, there will be certainly, if you look at it very carefully, there will be 4 vertices. Or there is one possibility that this one arc of the curve is actually a circle which contains infinitely many vertices. Okay. If you take points on a circle, what happens is that at all those points, you see, curvature is constant. Okay. Since curvature is constant, that's a local maximum and also global maximum and global minimum. So every point is a vertex, theoretically. If for a constant function, for a function, how do you get the critical points? Its derivative should vanish. If the curvature is constant, it's a constant function, the derivative of the curvature is 0. Therefore, every point is a critical point. And there are infinitely many points. And all I'm saying is I need only 4 points. So you see, if you are very careful that at these bends, you don't have an arc of a circle, okay, then somehow you will end up with getting 4 vertices. Okay. And you must also understand that when you go on a straight line, okay, when you go on a straight line also the curvature is 0. And there again the derivative of the curvature is 0. So those are all points of, again they are local extreme. So even a straight line is ruled out. The moment you have a segment of a straight line, okay, then all those points are vertices. If you have a portion which is consists of an arc of a circle, all those points are vertices, and there are infinitely many of them. So you have to be very careful never to move in a straight line, never to move in a circle, and do this. So you see, if you look at this picture, more or less I seem to have drawn a straight line like this, okay, and then all those points are vertices. Okay, there are infinitely many of them. So you should, if you cleverly try to draw a picture where you avoid drawing a straight line or you avoid drawing a circle and come back to the same point, you will see that in order to avoid drawing a straight line, you will have to, you will start moving left and right, and then you will introduce curves. Okay, and then when you move from left to right or right to left, then you will see that you will get maxima, minima. You see, vertices will appear automatically, and the point is about minimum number of vertices if you want to come back to the starting position, and that's 4. Okay, and so this can be rigorously proved, but of course this requires more formulation and mathematical rigor, but I am just trying to tell you intuitively what this is all about. Okay, no, if you define a vertex to be a point where the curvature has a local maximum or minimum, then if you take a straight line, along every point of the straight line the curvature is constant, and it is a local maximum or minimum by definition. A constant function is at every point having a local maximum or minimum, and it is, of course, every point is a critical point because the derivative is 0, because it's a constant function. So if you want a real example, you will have to avoid going in a straight line. You have to also avoid going in a circle. Yeah, it's important. See, as I told you, it's important that you must remember that you have to put enough conditions of differentiability. You are dealing with good functions. Since we are doing differential geometry which involves curvature, which is a second derivative, we always assume that the second derivative exists and is continuous. So that's already, they are called as C2 functions. Okay, so it should be C2. So there's without, of course, that differentiability condition, you cannot talk about the second derivative, and then you cannot understand curvature in geometric way. Okay, so this is about the four-vertex theorem. This is again something that we will cover, and I will do the, we will see how to do this. Okay, in the language of differential geometry. Okay, so this is a very interesting theorem. Then the next thing I want to tell you about is something more interesting about curves. Okay, there are several interesting things about curves that I want to tell you, which connect with things in daily life and with geometry. So let me tell you something about curves. Curious results about curves. Of course, I will say further, because this the four-vertex theorem and the isoperimetric inequality are also curious theorems about curves. Okay, which can be approached by differential geometry. So further curious results about curves. So there is one aspect of differential geometry that is very, very important, which comes up when you look at three-dimensional curves, space curves, in comparison with two-dimensional curves. Okay, so if you look at a two-dimensional curve, which is a curve in the plane, you have the idea of curvature. Okay, and but if you go to three-dimensional space, let's say, and look at a three-dimensional curve there, something we call it space curve. Okay, a curve that can be put in a plane is called a plane curve. It's called a two-dimensional curve. A curve that cannot be put in a plane but can live only in three space, that can be visualized only in three space, is called a three-dimensional curve or a space curve. Okay, the standard example is that of a helix, which is like a spring, okay, or the grooves of a nut or a screw. Okay, so what happens with three-dimensional curves? So in the case of two-dimensional curves, you have I told you that the curvature at a point is given by taking a best approximating circle and looking at that circle is called the circle of curvature. Its radius is called the radius of curvature, and then you take reciprocal of the radius of curvature. That's a curvature. Okay. Now for three-dimensional things, the situation is more complicated. So in the two-dimensional case, what is happening is, as you move along the curve, the circles are changing depending on how the curve is curving. Okay, the circles become smaller if it's curving more, and they become larger if it's curving less. Okay, but they are all circles lying on the plane with tangent, which are tangent to the curve at the corresponding points. But in three dimensions, something interesting happens. You have one more character that comes into the picture, and that is called torsion. Okay, so this is another very important concept that comes up in differential geometry. So in 3D, in 2D curves, study of 2D curves, you have only curvature. But if you go to 3D curves, there are two kinds of curvature. The first one is the usual curvature. The second one is called second curvature, which is kind of more commonly known as torsion. Okay, so you have curvature and torsion. So this is the new thing that comes. And as you can guess, if you try to get hold of torsion for a plane curve, you will get 0. There is no torsion for a plane curve. Exactly. Non-torsion curves are not plane. Yes. Okay. So the point is, what is this torsion all about? So you see, again, I am trying to give you a picture of what it is. See, if you take a curve in 3 dimensions, something like a coiled spring. Okay. If you take any point on the curve, okay, and try to fit a best fitting circle, okay. Of course, this best fitting circle will be a tangent to the curve at that point. But you see, now we are in space. Okay. assuming that there is a best fitting circle, okay, I can have many, around that point I can have so many circles in all 360 degree directions, right? So for example, if I want to have a circle, with this pencil as tangent, then at this point I can draw a circle like this and I can draw a circle on this side. I have only two choices if I fix the radius. But for a space curve, you see, I can draw that circle in so many ways, okay? Now the point is, what do you do in that case? So there's something interesting that happens. What happens is that if you want a particular circle, then it should lie on a particular plane, okay? And then what happens is, in the three-dimensional case, it so happens that there is a plane. There is a very special plane in which your circle of curvature lies. Okay, so there is attached to every point a plane, okay, on which you have the circle of curvature. And mind you, this is a plane in space, all right? And what is happening is that, so there is a plane in space and there is a circle on that plane, so it is uniquely determined, okay? So that is the term called osculating plane that is used, okay, osculating plane. Okay, and so what happens for a space curve is that, this circle of curvature is lying on a osculating plane. You can even make sense of what is called a sphere of curvature, okay, because it's you can even try to fit a sphere, okay. And then here is the interesting thing. The point is that this at that instant, a small portion of the curve, if you look at it, it appears as if it is in that plane, and for that plane, that is the circle of curvature. But still, this is not a curve which is on a plane. So what is going to happen is that this curve is going to escape from that plane. There is this tendency of this curve to escape from the plane at every point. That's what makes it a space curve. If that tendency is not there, then it will remain on the plane, okay, and that tendency, you try to measure it, that's the torsion, okay. And how do you measure that? You try to measure the normal to the curve. You try to measure a normal, okay. If the curve is on a plane, okay, the normal will always be constant. It will be normal to the plane, okay. But if this plane starts changing, the normal to the plane also starts changing, and you measure the change in that normal, okay. That gives you the torsion. So torsion measures the tendency with which the curve is trying to jump out of the plane at every point instantaneously. That's what makes it a space curve, okay. So that's what torsion is, okay. Now of course this is very, very qualitative, but there are explicit equations you can write using calculus and linear algebra. They are called the Frohn-Serre equations, okay, and they will involve further work that we will do, okay. So I will just say tendency of curve to escape from the plane is the torsion, okay. And so the most important thing is that if you take three-dimensional curves and two-dimensional curves, the two-dimensional curves have only curvature, three-dimensional curves have both curvature and torsion, okay. And then you can ask, well, now that you have this curvature and you have torsion, are they good enough for classification? Okay, so if two curves are you take a curve and then you translate it, or you apply what is called an isometric transformation. That is, you just take it and you just rotate it and translate it. It's just the same curve, but you have just moved the plane in which it is there, all right. And you can do this also to space curves, and you can see that if you do that, actually you are not changing anything. The curvature and torsion are all the same, okay. So if two curves are rigid motions of one another, then they should have the same curvature and torsion. If it is, of course, torsion will come up only if you are looking at three space curves. If it's only plane curves, it's only curvature. So if two curves are differing by rigid motion, what is a rigid motion? You can break it down into a translation followed by a rotation, or a rotation followed by a translation. these are rigid motions. They are called rigid motions because they don't change the geometry of the object. It's just that you are just changing the perspective from which you are looking at the object. Okay. In whatever perspective I look at a circle, it's always a circle. Okay. So so long as I am looking at it on a plane. Of course, if I look at it from a slant, in a slanted way, probably I may get something that looks like an ellipse. I'm not doing that. Okay. So you go by rigid motions, then curvature and torsion should be maintained. And here is the amazing thing. The converse is also true. If you have two curves, which plane curves which have the same curvature, then you should be able to rigidly move one to the other. Okay. That means plane curves are completely classified by the curvature. And you have to be a little bit careful. You have to worry about the orientation, and so you have to use what is called a signed curvature. That is a mathematical sign that you have to add to it. So the correct result would be that the plane curves are classified by curvature, signed curvature, and if you take space curves, they will be classified by curvature and torsion. So you get these classification theorems. After all, if you give me the shape of the curve, then I know the curve. What's the big deal? And rigid motion doesn't change the shape, right? So if two curves have the same shape, they should be literally the same. You should be able to move one to the other and superimpose one on the other by a rigid motion. And now all this looks, physically very, very, obvious, right? But then you have to prove it mathematically. And when you want to do it mathematically, you will have to get into the language of differential geometry. You have to write down, formulas for curvature, for torsion. And since the rigid motions are involved, you will have to involve yourself with representing these rigid motions by 3x3 matrices. And what happens is that the so-called orthogonal group will come in, the group of which is involved in the group of isometries of space. Okay, so a lot of linear algebra and beautiful geometry gets into the picture. Okay, and that mathematical part of it will also be done. Okay, so now, pardon me. Yeah, if you ask what happens if you do a mirror image, then what is going to happen is that the orientation is changed. Therefore, what you are doing is basically it's like changing the sign of the curvature. So, but you what happens with the torsion is that the torsion is measured by a handed system. Okay, and then the right-handed system will become a left-handed system when you do this mirror image. Okay, and of course all these things, the reflection in geometry, you can include reflection and you can exclude it. Okay, the only problem is that if you include reflections, then these are called as non-oriented isometries. If you want the orientation also to be preserved, then you don't include reflection, and they are called oriented isometries. So you have results for both. For plane curves, for example, if you take the mirror image, you will be changing the sign of the curvature. All right, but and for space curves, if you do that, you will be changing the right-handed coordinate system to a left-handed coordinate system. Okay. Yeah, I mean whatever notion of orientation that you want to think of, that will be changed. The orientation will be reversed. Okay, that's the only thing. Okay, so it's a question of whether you are going to preserve the orientation or whether you are going to reverse the orientation. Okay, and that can be written down because reflection is also given by a nice matrix. Okay, so the ideas of linear algebra will apply here. Okay, fine. So so let me again, continuing with interesting things connected with curves. Let me again go back to some nice physical questions. Okay, so okay, then I will stop. I should also give you enough time to rush out. So we will again.